All right, pre-calc. We are starting a unit on integers and polynomials. It's shorter than our last unit. There are about 7 lessons, so this should take us about 3, maybe 4 weeks to get through. Our first unit is all on factors of integers and polynomials, um, factoring in a sense. So we're going to start by defining different forms of polynomials. So um, as a just a quick review before I do any definitions, back in Algebra 2, you did talk about degrees of polynomials. That degree is always found by looking at the highest exponent of a of so it's looking at the term with the highest exponent of the polynomial. So what I'm going to do in here is I'm going to write the exponent form of a polynomial, which is in standard form. I'm going to put with coefficients in form an, and we could have like a -1, -2. It's just saying it is just to distinguish different terms. So the standard form of a polynomial goes from well, we're going to say p of x first. P of x equals a sub n x to the power of n, just being a term, plus a sub n minus 1 x to the power of n minus 1, plus a sub n minus 2 x to the power of n minus 2. And we keep subtracting until we get to the last two terms, which might look like a 1 x to the power of 1, which we don't have to write a power of 1, plus a sub 0, which would mean that a sub 0 is a constant term, with the only other condition being that a sub n, that leading coefficient, cannot equal 0. Otherwise, we would have a different type of polynomial. Within factored form, p of x is equal to the factors of the expanded form. So just as a quick example, that might look like p of x equals, and this is not by any means. In fact, I'm going to write ex there. Px might be something like x times x minus 2/5 times x plus 1/3. Those are factors of some other polynomial. So then I'm going to define what a factor is, and there's two forms we're going to look at. So first is for factors of a number, an integer. So suppose that n and d, so just two values, are integers and d cannot equal 0, period. D is considered a factor of n if and only if there is an integer q such that n is equal to q times d. Now, likewise, we can expand that from integers into polynomials if we say, suppose that n of x and d of x are polynomials and d of x is not the zero polynomial, meaning it doesn't equal 0. Then we can say d of x is a factor of n of x if and only if there exists a polynomial q of x such that, I'm just going to write, moving forward with pre-calc, I'm going to just shorthand ST as such that. You are welcome to do that as well. So there exists a polynomial q such that n of x is equal to q of x times d of x. So n of x is equal to the product of q of x and d of x. So let's look at an example. They're asking us if 5 is a factor of 25m minus 10n. So more importantly, they're asking us if 5 is a factor of the expression when m and n themselves are integers. So we know because m and n are integers, 25 and 10 are both integers, this expression itself represents an integer value. So to determine if 5 is a factor of this, we have to ask ourselves, can we write this where it is 5 times some expression? So it's kind of like asking us, can we divide 5 out of each term? Well, we can. 25m divided by 5 is 5m, minus 10n divided by 5 is 2n. So we can say because 5m minus 2n is an integer, because m and n are integers, and 5 times an integer will give us another integer, 2 times an integer will give us another integer. So because this is an integer, 5 is a factor of 25m minus 10n. All right, we're doing the same thing, but now they're asking us, is 13m squared n to the 7th a multiple of m to the 3rd n? So that's a little bit of a different question. So remember, factors are smaller things that make up a bigger part. Multiples are things that are bigger, made up of smaller things. So to see if it is a multiple, what we want to do is we're going to take the expression we're given, 13m squared n to the 7th, set it equal to, so a multiple of m to the 3rd n would mean I have to take m to the 3rd n, and I have to multiply it by some value that I'm going to call k. So I'm going to even off to the side say maybe even before this, I would say let k be a constant. So now we're going to want to solve this for k, because this would be a multiple if k is able to be an integer value or a whole number value. If it's a rational value, if it's a fraction of some sort, then we can't call it a multiple. So I'm going to isolate k by dividing by m to the third n on both sides. M to the third n. So k will equal 13. If I simplify this, I'm going to get rid of all the m's on top and be left with one m left on the bottom. And I can get rid of one n in both portions. So I have n to the sixth over m. 13 n to the sixth over m. Because of this, we can't guarantee that this would be an integer value. So let's find a value where k is not an integer. So when can k not be an integer? Well, so k can't be an integer if the denominator is not a factor of the numerator. So, as just an example, if we let n equal 1 and m equal 2, that would give us k equals 13 over 2, which is not an integer. So we can say, so 13 m squared n to the 7th is not always a multiple of m to the third n. It's possible that it is sometimes a multiple, but not always. All right, so now we're going to look at the transitive property of integer divisibility. So we phrase that as, for all integers, a, b, and c, comma, if a is a factor of b and b is a factor of c, comma, then a is a factor of c. It's just saying if b is divisible by a and c is divisible by b, then c is also divisible by a. That's all it's really saying. Okay, let's look at the transitive property of polynomial divisibility, very similar to the last one. We can say for all polynomials, a of x, b of x, and c of x, comma, if a of x is a factor of b of x, comma, and b of x is a factor of c of x, comma, then a of x is a factor of c of x. All right, so now we are going to be asked to factor the expression 6x to the 5th minus 15x to the 4th minus 10x to the 3rd plus 25x squared minus 4x plus 10. It's a lot. So to do this factoring, it really just comes with some experience of practicing. So there's a lot of different things we could do. We could, well, really what I'm going to do is I'm going to group these in chunks that I know I can factor a common factor out of and then factor them easily. So at a minimum, I need chunks that have two terms, but they can also be as long as I want them to be. So initially, when I was preparing for this, I was like, well, is there a way that I can cut this in half and factor it? I tried that. That didn't work. So there is no way to just cut this in half and look at each side and factor those separately. But then I asked, well, there are six terms. Can I cut this in thirds by grouping and then group terms um, that I know have something in common? So that worked. So I grouped this, the first and second term, the third and fourth term, and then the last two terms. And then I factored something out of each separate pair of terms. So I know with this first one, 6 and 15, they are both divisible by 3. So I can factor out a 3 for sure. And both terms have at least x to the fourth. So I can factor an x to the fourth out as well, giving me a 2x minus 5. So then with the second pair, I noticed 10 and 25 are both divisible by 5. Now, if I want to really, in the end, my goal is to try to get this 2x minus 5 in each pair. So I'm going to write a plus because I know I've got another pair here, but I want this first term in the parentheses to be positive. Well, the first term up here is negative. So I also need to factor out a negative. So I'm going to go negative 5 because I know that works. And then they both have at least x squared, so I'm going to factor out x squared as well. So what's left, if I divide negative 10x cubed by negative 5x squared, I get 2x. 25x squared divided by negative 5x squared gives me a minus 5. Ooh, I see something happening. Let's hope we can get this 2x minus 5 in this last grouping as well. So write a plus because I've got another pair. And I'm going to do two parentheses, see if there's something that I can take out of negative 4x plus 10. Well, they're both divisible by 2. And because I want this first term to be positive, I'm going to make that factor out with negative 2. So negative 4x divided by negative 2, that gives me 2x. 10 divided by negative 2 gives me minus 5. Well, now each term has 2x minus 5. So I'm going to factor that out of everything. I'm going to have 2x minus 5 times, in this first term, I'd still have 3x to the fourth minus 5x squared minus 2. Well, this is a trinomial where the middle term's exponent on x is half of the leading exponent. So I can use the x method to try to factor, to see if I can factor this trinomial. So up on top, remember, I go a times c, which in this case would be negative 6. Down below, I would take my b term, negative 5. When I have a negative up top, I know I have to have a plus and a minus in my factors. To multiply to make 6 and add to make 5. Well, factors of 6 are 6 and 1 and 3 and 2. Right now, I'm just checking which one gives me some form of 5. Well, 6 minus 1 is positive 5. Okay, 3 minus 2 is positive 1. If I flip the signs, make this side the negative, make this side the positive, negative 6 plus 1, that gives me the negative 5 I want. So I'm also still doing a little bit of side work before I put my factors here. I set up both factors as 3x squared. That is a key to this one because I'd have to take half of that x to the fourth. Minus 6 and 3x squared plus 1. So I now ask, within each set of parentheses, is there something other than 1 I can divide out? Well, in this first one, I can divide both terms by 3, giving me an x squared minus 2. I can't divide anything out of that last one. So all my factors, 2x minus 5, I've got x squared minus 2. There's no more I can factor for that. That's not a difference of squares. 2 is not a perfect square. And then 3x squared plus 1. Those are all the factors of that polynomial we were given. 6x to the 5th minus 15x to the 4th minus 10x to the 3rd plus 25x squared minus 4x plus 10. Okay, we've got 2 theorems to wrap up this lesson, and then we are done. So we've got the factor of an integer sum is our first of these last 2 theorems. That states for all integers, a, b, and c, comma, if a is a factor of b and a is a factor of c, comma, then a is a factor of b plus c. So then likewise for the factor of a polynomial sum, we can state if a of x is a factor of b of x and a of x is a factor of c of x, comma, then a, and I should rephrase that as a of x. I've written it correctly, but I might have been saying it incorrectly. A of x is a factor of b of x plus c of x. And that's going to wrap up our first lesson in this integers and polynomials unit.